Hey, welcome to the Night Scientist of the Universe. I'm so happy you're here with me today. You know, there's something truly magical about settling in for a gentle exploration of the world around us. Whether you're curled up in your favorite chair with a warm cup of tea, lying in bed as the day winds down, or simply taking a quiet moment to yourself, I want you to know that this is your time. A time to let your mind wander, to discover something beautiful, and to find that sense of wonder that maybe got tucked away somewhere in the busy rhythm of everyday life. I've always believed that the most extraordinary discoveries happen when we slow down just enough to really see what's been right in front of us all along. And today, we're going to embark on one of those journeys together. We're going to explore something so familiar, so everyday, that you might never have stopped to think about just how absolutely miraculous it really is. Something that sits quietly in your bathroom, hangs on your bedroom wall, or rests in your pocket, faithfully doing its job without any fanfare or recognition. Today, we are diving into the fascinating world of the story of a mirror, light in reverse. We're going to uncover the gentle mysteries of reflection, discover how light dances and plays in ways that would make the most skilled ballet seem clumsy by comparison, and learn about the incredible physics that happens every single time you glance at your reflection. But don't worry, we won't be diving into complex equations or overwhelming technical jargon. Instead, we'll explore this world the way a storyteller might, with wonder, curiosity, and the kind of gentle pace that lets every beautiful detail sink in. Picture this, somewhere in the distant past, perhaps millions of years ago, an early human knelt beside a still pool of water. The morning sun was just beginning to cast its gentle light across the landscape, and the water was perfectly calm, like a sheet of liquid glass. And then, for the first time in this person's life, they looked down and saw something that must have seemed like pure magic. There, staring back at them from the depths of the water, was another face, their own face, but somehow existing in this mysterious underwater world. Can you imagine that moment? The confusion, the wonder, the probably instinctive reach toward the water that would have shattered the image into 1,000 ripples. This was humanity's first conscious encounter with reflection, and it must have felt like discovering an entirely new dimension of reality, because in a way, that's exactly what it was. You see, reflection isn't just about seeing yourself. It's about light itself performing one of the most fundamental dances in the universe. Every time you look in a mirror, you're witnessing photons, those tiny packets of light energy, executing a perfect choreography that has been happening since the very first star began to shine. These photons travel from their source, perhaps the bulb in your bathroom or the sun streaming through your window, and they embark on what we might call their final journey. But here's where it gets truly magical. When these photons reach the surface of your mirror, they don't just disappear or get absorbed. Instead, they perform what physicists call specular reflection, but what I like to think of as light's most elegant dance move. They bounce off the surface at precisely the same angle they arrived, as if the mirror is a perfect dance partner that knows exactly how to match their movement. This isn't random. This isn't accident. This is one of the most reliable laws of physics, happening billions of times per second. Every single time you glance at your reflection, think about what this means for a moment. The light that left the sun 8 minutes ago, traveling at 186,000 miles per second through the vacuum of space, hitting your skin and bouncing off in all directions. Some of those photons finding their way to your mirror, bouncing off at the perfect angle and then traveling to your eyes where they create the image you see as yourself. The light that reveals your reflection has been on an incredible journey, and you are both the source and the destination of that journey. But let's slow down even more, because there's something almost poetic about what's happening here. When you look at your reflection, you're literally seeing yourself in the past. Not the distant past, mind you, but the past nonetheless. Light, even traveling at its incredible speed, still takes time to make that journey from you to the mirror and back to your eyes. It's just a few nanoseconds, but it's measurable time. So every reflection you see is actually a glimpse of who you were a few moments ago, preserved in light and delivered back to you through the magic of reflection. This is why mirrors have always held such a special place in human culture and mythology. They're not just tools for checking our appearance. They're portals that show us a version of ourselves that exists in a slightly different time and space. Ancient civilizations understood this intuitively, even if they didn't have the scientific language to describe it. They made mirrors from polished metal, from obsidian, from any surface that could perform this magical reversal of light. The ancient Egyptians crafted mirrors from polished copper and silver, believing they could reveal not just physical appearance, but spiritual truths. The Greeks and Romans used mirrors in their temples, understanding that reflection was somehow connected to the divine nature of light itself. In many cultures, mirrors were thought to be windows to other worlds, and when you really think about the physics of what's happening, they weren't entirely wrong. A mirror does show you another world, a world where everything is reversed, where your left hand becomes your right hand, where text becomes unreadable, where the familiar becomes mysteriously foreign. Before we can truly understand the story of a mirror, we need to understand the star of our story, light itself. And light, my friend, is far more mysterious and wonderful than most people realize. It's not just the stuff that lets us see. It's not just the brightness that fills our rooms or the sunshine that warms our faces. Light is both a wave and a particle, both energy and matter, both the fastest thing in the universe and the most fundamental building block of reality itself. Imagine, if you will, a wave on the ocean. You can see it rolling toward the shore, building in height, carrying energy from far out at sea. But you can also think of it as individual water molecules, each one moving in its own circular path, each one carrying its own tiny bit of energy. Light is remarkably similar. It behaves like a wave, with peaks and troughs, with frequency and wavelength, with all the mathematical elegance that waves possess. But it also behaves like particles, tiny packets of energy called photons, each one carrying its own quantum of light energy. This wave-particle duality puzzled scientists for centuries, and honestly, it still puzzles us today. How can something be both a wave and a particle? How can light behave like water ripples when we're looking at it one way, and like tiny bullets when we're looking at it another way? The answer is that light is neither and both. It's something entirely unique, something that exists in a realm of physics that our everyday experience doesn't prepare us for. When light behaves like a wave, it has properties that might remind you of sound waves or water waves. It has a frequency, which determines its color, and a wavelength, which is the distance between one wave peak and the next. Red light has a longer wavelength than blue light, which is why red light can travel through fog better than blue light. It's also why sunsets are red and orange. The shorter blue wavelengths get scattered away by the atmosphere, leaving the longer red wavelengths to paint the sky in warm colors. But when light behaves like a particle, each photon carries a specific amount of energy that depends on its frequency. Higher frequency light, like blue and violet, carries more energy per photon than lower frequency light, like red and orange. This is why ultraviolet light can give you a sunburn while infrared light just warms you up. The UV photons carry enough energy to actually damage the molecules in your skin, while the infrared photons just make the molecules vibrate a little faster, which we experience as heat. Now, here's where it gets really interesting for our story. About mirrors. When light hits a surface, the way it behaves depends on the properties of both the light and the surface. Some surfaces absorb light, converting the light energy into heat. Think of a black asphalt road on a sunny day, soaking up the sunlight and becoming hot to the touch. Other surfaces transmit light, allowing it to pass through. Think of a clear window, letting the sunlight stream into your room virtually unchanged. But mirrors do something special. They reflect light, bouncing it back in a very specific way. And the key to understanding how mirrors work is understanding that light always obeys what we call the law of reflection. When a beam of light hits a mirror, the angle at which it bounces off is exactly equal to the angle at which it arrived. If light hits the mirror at a 30-degree angle, it will bounce off at a 30-degree angle. But on the opposite side of what we call the normal line, the imaginary line that's perpendicular to the mirror's surface, this law of reflection is so fundamental, so reliable, that it happens every single time without exception. It doesn't matter if the light is coming from the sun, from a candle, from an LED bulb, or from a firefly. It doesn't matter if the mirror is made of silver, aluminum, or any other reflective material. The law of reflection is as constant as gravity, as predictable as the rising of the sun, as unchanging as the passage of time itself. But light has other properties that make the story of mirrors even more fascinating. Light carries information. Every photon that bounces off your face and into a mirror carries information about the color of your eyes, the texture of your skin, the shape of your smile. When that photon bounces off the mirror and enters your eye, it delivers that information to your brain, which reconstructs the image you see as your reflection. Think about what an incredible process this is. Light is essentially a messenger, carrying detailed information about the world around us. When photons bounce off a red rose, they carry information about the rose's redness. When they bounce off a mirror, they carry information about the mirror's smoothness and reflectivity. When they bounce off your face, they carry information about your unique features, your expressions, your very essence as a human being. Let's imagine we could shrink down to the size of a photon and experience the world from light's perspective. Picture yourself as a tiny packet of energy, born perhaps in the nuclear furnace of the sun, where hydrogen atoms are being fused into helium at temperatures of millions of degrees. You begin your existence as pure energy, and your very first journey is the long, slow struggle from the sun's core to its surface. A journey that takes thousands of years as you're absorbed and re-emitted by atom after atom. Finally, you escape the sun's surface and begin your 8-minute journey through space at the speed of light. There's nothing to slow you down out here in the vacuum, nothing to absorb you or scatter you. You travel in a perfectly straight line at 186,000 miles per second, covering the 93 million miles from the sun to Earth in just over 8 minutes. You are pure energy in motion, a wave of electromagnetic radiation carrying the warmth and light that makes life possible on our planet. You enter Earth's atmosphere and begin to interact with the molecules of air. Some of your fellow photons gets scattered by tiny particles in the atmosphere. This is what makes the sky appear blue during the day and red at sunset. But you continue on your path, perhaps passing through a window and entering a room where a person is standing in front of a mirror, getting ready for their day. You strike the person's face, and suddenly your journey takes on new meaning. The atoms in their skin absorb your energy and immediately re-emit it. But now you carry information about the color and texture of their skin. You've become a messenger, carrying the story of what you've encountered. You bounce off their face at countless different angles, some of you heading toward their eyes, some toward the walls, some toward the mirror that hangs on the opposite. Well, let's follow the photons that head toward the mirror. You approach this strange, smooth surface, and as you get closer, you begin to interact with the electrons in the metal atoms that make up the mirror's reflective coating. These electrons are arranged in what physicists call a sea of electrons, and they're incredibly mobile, able to move freely throughout the metal structure. When you arrive at the mirror's surface, your electromagnetic field begins to interact with these electrons. The electrons start to oscillate in response to your electric field, and as they oscillate, they generate their own electromagnetic field. This is the crucial moment in the dance of reflection. The electrons are essentially catching your energy and throwing it back, but they're doing so in a very specific way that preserves both your energy and your information. The remarkable thing is that this process happens so quickly, so smoothly, that you don't lose any of your energy or information. You bounce off the mirror at exactly the same angle you arrived, carrying the same information about the person's face, the same energy you've carried since leaving the sun. You are now headed back toward the person, but from a different angle, carrying the same message but delivering it from a new perspective. When you enter the person's eye, you begin the final phase of your incredible journey. You pass through the clear cornea, through the aqueous humor, through the pupil, and finally reach the retina at the back of the eye. Here, you encounter specialized cells called photoreceptors, and your energy is absorbed by molecules called rhodopsin. This absorption triggers a cascade of chemical reactions that ultimately send an electrical signal to the brain. And there, in the visual cortex of the brain, the information you've carried is decoded and interpreted. The brain takes the signals from millions of photoreceptors and reconstructs them into the image the person sees as their reflection. In a sense, you've helped create a map of light and shadow, color and texture, that the brain interprets as a face, as a person, as a self. But the story doesn't end there, because reflection is happening continuously, billions of times per second. Every moment, countless photons are making this same journey, bouncing off the person's face, hitting the mirror, and returning to their eyes. The reflection you see is not a static image, but a constantly updating stream of information. A real-time movie created by the dance of light. This is why your reflection moves when you move, why it changes when you change expressions, why it perfectly mirrors your every gesture. It's not magic, it's the physics of light operating at incredible speed and precision. Every slight movement of your head changes the angles at which photons bounce off your face and into the mirror, creating a new pattern of reflected light that your eyes detect as movement in your reflection. Consider what happens when you smile at yourself in the mirror. The change in your facial expression alters the way light bounces off your face. The curves of your smile create different angles of reflection. The brightness in your eyes changes the intensity of the light being reflected, and even the slight flush of warmth that might come to your cheeks affects the spectrum of light that bounces back. All of these changes are instantly communicated to the mirror by the photons bouncing off your face, and just as instantly communicated back to your eyes by the photons bouncing off the mirror. The story of a mirror is really the story of what happens when light meets matter in the most perfect way possible. To understand this, we need to think about the different ways light can interact with the materials it encounters. Most of the time, when light hits something, one of three things happens. It gets absorbed, it gets transmitted, or it gets reflected. But mirrors are special because they're designed to reflect light as efficiently as possible, with minimal absorption or transmission. Let's start with absorption, because it's probably the most common thing that happens to light. When you wear a black t-shirt on a sunny day, you're experiencing light absorption. The pigments in the black fabric absorb photons across the entire visible spectrum, converting the light energy into heat energy. This is why black objects get hot in the sun. They're very efficient at absorbing light and converting it to heat. The absorbed photons essentially disappear as light, their energy transformed into the random motion of atoms and molecules that we experience as temperature. Transmission is what happens when light passes through transparent materials like glass or water. The photons interact with the atoms in the material, but instead of being absorbed, they're briefly absorbed and then re-emitted in the same direction. This process happens so quickly that the light appears to pass straight through, though it might be slowed down slightly. This is why a stick looks bent when you put it in water. The light coming from the stick is slowed down as it passes through the water, changing its direction slightly. But reflection is something special. When light hits a mirror, it encounters a surface that's been specifically designed to bounce light back with maximum efficiency. The key to this efficiency lies in the atomic structure of the mirror itself. Most mirrors are made by coating a piece of glass with a thin layer of metal, usually aluminum or silver. These metals have a special property. They have what physicists call a sea of free electrons. These free electrons are not bound to any particular atom. Instead, they can move freely throughout the metal structure, like a fluid made of electrical charge. When light hits this surface, the oscillating electric field of the light wave pushes these electrons back and forth. The electrons respond by oscillating at the same frequency as the incoming light. And as they oscillate, they generate their own electromagnetic field, which is the reflected light. This process is incredibly efficient because the electrons can respond almost instantaneously to the incoming light. There's no delay, no energy loss, no distortion of the signal. The reflected light carries exactly the same information as the incoming light, just traveling in a different direction. This is why mirrors give us such clear, undistorted images. They're not just bouncing light back randomly, they're preserving every detail of the light's original message. But there's something else happening at the mirror's surface that's even more fascinating. The smoothness of the mirror is crucial to its function. If you look at a mirror under a powerful microscope, you'll see that its surface is incredibly smooth, much smoother than almost any other surface you encounter in daily life. This smoothness is measured in wavelengths of light. For a mirror to produce a clear reflection, its surface irregularities must be much smaller than the wavelength of visible light. Visible light has wavelengths, ranging from about 400 to 700 nanometers. A nanometer is 1/1000th of a meter. So we're talking about incredibly small distances. The surface of a good mirror has irregularities of only a few nanometers, making it one of the smoothest surfaces humans have ever created. This smoothness ensures that light rays hitting the mirror at the same angle will all be reflected at the same angle, preserving the coherence of the reflected image. Compare this to a rough surface like a piece of paper or a painted wall. When light hits these surfaces, it gets scattered in many different directions because the surface has irregularities that are much larger than the wavelength of light. Each tiny bump and valley on the surface acts like a tiny mirror oriented at a different angle, so the reflected light goes off in many different directions. This is called diffuse reflection, and it's why you can't see your reflection in a piece of paper, even though the paper is reflecting just as much light as a mirror. The manufacturing of mirrors is therefore a delicate process that requires incredible precision. The glass substrate must be perfectly flat, the metal coating must be evenly applied, and the entire surface must be protected from scratches and corrosion. Even the slightest imperfection can create distortions in the reflected image, which is why high-quality mirrors are so expensive, and why they need to be handled with such care. There's also something poetic about the fact that mirrors work by harnessing the fundamental properties of electrons, these tiny particles, which are essential to all chemical reactions, to all electrical currents, to all of life itself, are also the key to reflection. When you look in a mirror, you're seeing the result of billions of electrons dancing in response to light, creating a perfect replica of the light that hit them. In a sense, your reflection is created by the same fundamental forces that power your brain, your heart, and every cell in your body. This brings us to one of the most beautiful aspects of mirror physics, the concept of virtual images. When you look in a mirror, the image you see appears to be behind the mirror, at the same distance behind the mirror as you are in front of it. But of course, there's nothing actually behind the mirror. The image is what physicists call a virtual image, created by the way our brains interpret the reflected light rays. Your brain assumes that light travels in straight lines, which is true most of the time. So when reflected light enters your eyes, your brain traces those light rays backward in straight lines to determine where the light must have come from. Since the light rays have been reflected by the mirror, your brain traces them to a point behind the mirror, creating the illusion that there's another version of you standing in that impossible space behind the mirror's surface. This virtual image has some interesting properties. It's the same size as you, but it's laterally inverted, meaning left and right are flipped. It's also the same distance behind the mirror as you are in front of it, and it appears to be even though it's created by light reflecting off a flat surface. This virtual image is so convincing that it can be startling when you first encounter it, which is why babies often react with surprise and delight when they first see themselves in a mirror now. As we settle deeper into our exploration of mirrors and light, imagine if you could shrink yourself down to the size of a single atom and watch what happens when a tiny particle of light approaches a mirror's surface. What you would witness is one of the most elegant dances in all of physics. A choreography so precise and beautiful that it has captivated scientists for generations. Picture this microscopic world where a single photon, traveling at the speed of light, approaches the silvered surface of a mirror. This photon isn't just a simple particle bouncing off like a rubber ball hitting a wall. Instead, it's engaged in a quantum conversation with the electrons in the mirror's metallic coating. The photon carries with it a specific amount of energy, a particular wavelength, and what we might call a quantum signature that determines exactly how this interaction will unfold. When our photon reaches the mirror's surface, something truly remarkable happens. The photon doesn't simply bounce off the first layer of atoms it encounters. Instead, it penetrates slightly into the metal. Typically, just a few nanometers deeper distance, so small that millions of them would fit across the width of a human hair. In this infinitesimal space, the photon interacts with the sea of free electrons that exists within the metal structure. These electrons, you see, are not bound to any particular atom. They flow freely through the metal like a fluid, and this freedom is what gives metals their unique properties. When our photon enters this electron sea, it creates what physicists call a surface plasman, a collective oscillation of electrons that ripples through the metal surface like waves on a pond. The photon's energy is temporarily absorbed by these electrons, causing them to vibrate in harmony with the light wave's frequency. But here's where the magic truly begins. These oscillating electrons don't hold onto the photon's energy for long. Within an incredibly short time, we're talking about timescales measured in attosecons, which are 2 seconds, what seconds are to about 32 billion years. The electrons release this energy back out as a new photon. This new photon emerges from the mirror, traveling in the opposite direction, carrying with it the same energy, the same wavelength, and the same quantum properties as the original photon that entered. This process happens not just once, but simultaneously for billions upon billions of photons that make up the light waves we see. Each photon undergoes this quantum dance individually, yet they all emerge in perfect synchronization, maintaining the coherence of the original light wave. It's like watching a vast orchestra where each musician plays their part individually, yet together they create a harmonious symphony. The beauty of this process lies in its fundamental reversibility. The physics that governs how light interacts with a mirror is time-symmetric, meaning that if you could somehow reverse the flow of time, the process would look exactly the same. The photon that emerges from the mirror is, in every measurable way, identical to the one that entered, just traveling in the opposite direction. This is why we say that mirrors don't just reflect light, they reverse it, creating a perfect temporal mirror image of the electromagnetic field. What makes this even more fascinating is that this quantum interaction depends heavily on the specific properties of the mirror's surface, the type of metal used, its purity, the smoothness of the surface, and even the crystal structure of the atoms all play crucial roles in determining how efficiently this photon dance occurs. A perfect mirror would reflect 100% of the light that hits it, but in reality, even the best mirrors absorb a tiny fraction of the light energy, converting it to heat through interactions with imperfections in the metal structure. As we observe this quantum ballet from our imaginary vantage point, we begin to understand that reflection is not a simple mechanical process, but rather a sophisticated quantum mechanical phenomenon. The mirror doesn't just throw light back like a wall throws back a ball. Instead, it engages with light in a conversation conducted in the language of quantum mechanics, where energy is exchanged, electrons dance in harmony, and photons are reborn in perfect reverse. One of the most intriguing aspects of this quantum dance is the question of time. How long does it take for a photon to be reflected from a mirror? This might seem like a simple question, but it opens up a fascinating world of physics that challenges our everyday understanding of cause and effect. Let's imagine we're timing this process with the most precise clock in the universe. A photon approaches our mirror at the speed of light, 299,792,458 meters per second. This is not just fast. It's the ultimate speed limit of the universe, the speed at which causality itself propagates. Yet when our photon reaches the mirror, it doesn't instantly bounce back. Instead, it begins that quantum conversation we just explored. The time it takes for this entire process from the photon's initial contact with the mirror to its emergence as a reflected photon is incredibly short, but it's not zero. This duration is called the reflection time or dwell time, and measuring it has become one of the most challenging and fascinating pursuits in modern physics. We're dealing with timescales so brief that they make the blink of an eye seem like an eternity. To put this in perspective, imagine if we could slow down time so that 1 second lasted as long as the entire age of the universe, roughly 13.8 billion years. Even at this impossibly stretched timescale, the reflection time would last only about as long as it takes you to read this sentence. Yet within this infinitesimal moment, an entire universe of quantum interactions unfolds. During this brief interval, the photon doesn't simply pause at the mirror's surface. Instead, it exists in a quantum superposition state, where it simultaneously has properties of both the incoming and outgoing photon. This is one of those quantum mechanical concepts that seems to defy our everyday logic, yet it's been confirmed through countless experiments. The photon is, in a very real sense, both coming and going at the same time until the quantum interaction is complete. Scientists have developed ingenious ways to measure these incredibly short time intervals. One method involves using what's called attosecond pulses, bursts of light so brief that they can freeze even the motion of electrons within atoms. By firing these ultra-short pulses at mirrors and measuring the slight delays in the reflected light, researchers have been able to probe the temporal structure of reflection itself. What they've discovered is that the reflection time depends on several factors: the angle at which light hits the mirror, the material the mirror is made from, and even the color of the light all influence how long this quantum interaction takes. Red light, with its longer wavelength, tends to have a slightly different reflection time than blue light. This difference is so small that it would be completely imperceptible to us, yet it reveals the deep quantum nature of the reflection process. Perhaps most remarkably, this finite reflection time means that when you look at yourself in a mirror, you're not seeing yourself as you are at this exact moment. You're seeing yourself as you were a few attosecons ago. Of course, this delay is so brief that it's utterly meaningless on human timescales. It's trillions of times shorter than the time it takes light to travel from the mirror to your eyes. Yet from the perspective of the quantum world, this delay represents a fundamental aspect of how light and matter interact. This concept of reflection time also helps us understand why mirrors seem to create such perfect images. The quantum mechanical process that governs reflection is incredibly consistent and predictable. Each photon that hits the mirror undergoes essentially the same quantum interaction, experiencing the same brief delay and emerging with the same properties. This uniformity is what allows millions of photons to work together to create the coherent, reflected image we see. The precision of this process is truly astounding. If reflection were a random or chaotic process, mirrors would produce fuzzy, distorted images. Instead, the quantum mechanical nature of reflection ensures that each photon emerges from the mirror with mathematical precision, maintaining the exact phase relationships necessary to reconstruct a perfect image. It's as if nature has built into the very fabric of reality a mechanism for preserving and reversing light with extraordinary fidelity. As we continue our gentle journey into the world of mirrors and light, let's turn our attention to something you've probably noticed but might not have thought deeply about: the way colors appear in mirrors. When you look at a rainbow in a mirror, or observe the rich hues of a sunset reflected in a calm lake, you're witnessing a beautiful demonstration of how different wavelengths of light interact with reflective surfaces. Each color of light, from The deep reds to the brilliant violets has its own unique wavelength, its own frequency, and its own quantum signature. When these different colors approach a mirror, they don't all behave exactly the same way. While the differences are subtle, they reveal fascinating aspects of the physics of reflection that help us understand the deeper nature of light itself. Let's imagine we're watching a beam of white light which contains all colors mixed together as it hits our mirror. What appears to be a single beam of light is actually a symphony of different wavelengths, each carrying its own energy and each interacting with the mirror's surface in its own unique way. Red light, with its longer wavelength and lower energy, penetrates slightly deeper into the metal surface than blue light, which has a shorter wavelength and higher energy. This difference in penetration depth means that red and blue light experience slightly different quantum interactions with the electrons in the mirror. Red light tends to interact with electrons deeper in the metal structure, while blue light primarily interacts with electrons closer to the surface. These different interaction zones result in subtly different reflection characteristics for each color. Most high-quality mirrors are designed to reflect all visible colors with nearly equal efficiency, which is why the image you see in a mirror appears to have the same color balance as the original. However, if you were to examine the reflection with extremely sensitive instruments, you would find that different colors are reflected with slightly different efficiencies. This variation is typically less than 1%, but it's enough to reveal the quantum mechanical nature of the reflection process. The fascinating thing is that this wavelength dependence of reflection is not just a curious detail, it's fundamental to how we see and understand color. The fact that mirrors can preserve color information so faithfully is a testament to the precision of the quantum mechanical reflection process. If mirrors significantly favored one color over another, the world would look very different when viewed in reflection. Some specialized mirrors, however, are designed to be selective about which colors they reflect. These dichroic mirrors can reflect certain wavelengths while transmitting others, creating beautiful color effects that are used in everything from theatrical lighting to scientific instruments. These mirrors demonstrate that by carefully controlling the structure and composition of the reflective surface, we can tune the quantum interaction to favor specific colors. When sunlight hits a dichroic mirror, for instance, it might reflect only the blue and green wavelengths while allowing red and yellow to pass through. This selective reflection occurs because the mirror's structure, often consisting of multiple thin layers of different materials, creates constructive interference for some wavelengths and destructive interference for others. It's like creating a quantum filter that allows certain colors to participate in the reflection dance while excluding others. This wavelength selectivity also explains why some natural reflective surfaces, like the iridescent wings of butterflies or the shimmering scales of fish, can produce such brilliant colors. These surfaces contain microscopic structures that act as natural dichroic mirrors, selectively reflecting certain wavelengths while suppressing others. The result is colors that seem to glow with an inner light, created purely through the quantum mechanical interaction of light with carefully structured surfaces, even in ordinary mirrors. The slight wavelength dependence of reflection plays a role in the subtle color shifts we sometimes observe. If you've ever noticed that mirrors in older buildings sometimes give reflections with a slightly different color cast, you're seeing the result of age-related changes in the mirror's surface that affect different wavelengths differently. As the silvered backing of a mirror ages, it may develop microscopic irregularities that affect the reflection of different colors to varying degrees. This relationship between wavelength and reflection also helps explain why mirrors work so well. Across the entire visible spectrum, the quantum mechanical properties of metals like silver and aluminum are such that they interact efficiently with photons across the entire range of wavelengths our eyes can detect. This isn't a coincidence, it's the result of the specific electronic structure of these metals, which creates a window of high reflectivity that just happens to match the wavelengths of visible light. As we delve deeper into the quantum world of reflection, we encounter one of the most elegant and mysterious aspects of light: polarization. This property of light, invisible to our eyes but fundamental to how light behaves, reveals another layer of complexity in the seemingly simple act of reflection. Imagine light as a wave oscillating as it travels through space. But unlike a wave on a string, which can only move up and down, light waves can oscillate in any direction perpendicular to their direction of travel. They can vibrate vertically, horizontally, or at any angle in between. This direction of oscillation is what we call the polarization of light. When unpolarized light with waves oscillating in all directions, hits a mirror, something remarkable happens. The mirror doesn't treat all directions of oscillation equally. Instead, it has a slight preference for certain orientations, and this preference becomes more pronounced as the angle of incidence increases. This phenomenon, known as the polarization of reflected light, was discovered by the Scottish physicist David Brewster. In the early 19th century, picture yourself standing by a calm lake at sunset. As you look at the water's surface, you notice that the reflection of the sun creates a bright glare. This glare is not just intense light that has become partially polarized by the reflection process. The horizontal component of the light waves is preferentially reflected, while the vertical component tends to be transmitted into the water. This is why polarized sunglasses, which block horizontally polarized light, can dramatically reduce the glare from reflective surfaces. This polarization effect reveals the vector nature of light, the fact that light is not just a simple wave, but a wave with a specific direction of oscillation. When light reflects from a surface, both the electric and magnetic components of the electromagnetic wave must satisfy specific boundary conditions at the interface between air and the reflective material. These boundary conditions are different for light polarized parallel to the surface versus light polarized perpendicular to the surface. The quantum mechanical explanation for this polarization selectivity lies in how the oscillating electric field of the light wave interacts with the electrons in the reflective surface. When light polarized parallel to the surface hits the mirror, the electric field tends to drive electrons along the surface of the metal. When light polarized perpendicular to the surface hits the mirror, the electric field drives electrons into and out of the surface. These different types of electron motion result in different coupling efficiencies and thus different reflection characteristics. At a special angle called Brewster's angle, named after its discoverer, something extraordinary happens. Light polarized parallel to the surface is completely transmitted through the interface, while light polarized perpendicular to the surface is partially reflected. This means that at this specific angle, the reflected light becomes completely polarized. For a typical glass surface, this angle is about 56 degrees from the normal to the surface. This complete polarization at Brewster's angle is not just a curious phenomenon, it's a fundamental consequence of the electromagnetic nature of light and the way it interacts with matter. The angle at which this occurs depends on the refractive index of the material, providing a beautiful connection between the optical properties of materials and the quantum mechanical behavior of light. The polarization properties of reflected light have practical applications that touch our daily lives. The anti-glare coatings on eyeglasses work by creating destructive interference for light of certain polarizations. Photographers' polarizing filters use this principle to reduce reflections from water and glass surfaces. Even the LCD screens in our phones and computers rely on polarized light to create the images we see. But perhaps most beautifully, the polarization of reflected light helps us understand the fundamental wave nature of light itself. The fact that light can be polarized, and that reflection can change this polarization, provides compelling evidence that light is indeed a wave phenomenon. This wave nature, combined with the quantum mechanical properties we've explored, creates the rich tapestry of behavior that makes light so fascinating to study. When you look at your reflection in a mirror, you're seeing the result of countless quantum interactions, each one respecting the polarization properties of the light waves involved. The image you see is not just a reversal of light. It's a complex quantum mechanical reconstruction that preserves not only the intensity and color of the original light, but also its polarization characteristics. This preservation is what allows mirrors to create such faithful reproductions of the visual world around us. As we continue our exploration of the quantum world of mirrors, let's turn our attention to the surface itself, that critical interface where light meets matter and the magic of reflection unfolds. The quality of this surface, down to the atomic level, plays a crucial role in determining how perfectly a mirror can perform its quantum dance with light. Imagine you could examine a mirror's surface with an atomic microscope, zooming in until individual atoms come into view. What you would see is not the perfectly smooth surface that appears to your eyes, but a landscape of atomic hills and valleys. Even the finest mirrors have surfaces that are rough on the atomic scale, with irregularities and imperfections that affect how light interacts with the surface. These microscopic imperfection scratches, invisible to the naked eye, clusters of atoms that protrude slightly from the surface, or tiny pits where atoms are missing all influence the quantum mechanical interaction between light and the mirror. Each imperfection acts like a small scattering center, causing some photons to be reflected in slightly different directions than they would be from a perfectly smooth surface. The remarkable thing is that for most purposes, these imperfections are so small that they don't significantly affect the quality of the reflection. The wavelength of visible light is much larger than typical atomic scale irregularities, so most light waves see the surface as smooth on average. This is similar to how ocean waves, which are much larger than the pebbles on a beach, don't. Notice the individual stones as they wash over the shore. However, when we examine reflection more closely, we can detect the subtle effects of surface imperfections. Some of the light that hits the mirror undergoes what's called diffuse reflection. Instead of being reflected in a single, well-defined direction, it's scattered in many directions. This scattered light is usually much weaker than the main reflected beam, but it can be detected with sensitive instruments. The ratio of diffuse to specular mirror-like reflection depends on the surface roughness compared to the wavelength of light. This relationship is described by a parameter called the surface roughness parameter, which compares the height of surface irregularities to the wavelength of the incident light. When this parameter is small, the surface acts as a good mirror. When it's large, the surface becomes a diffuse reflector, scattering light in all directions. The process of creating a high-quality mirror involves carefully controlling surface roughness at the atomic level. Modern mirror-making techniques can produce surfaces that are smooth to within a few nanometers, about 20 atoms wide. This level of perfection is achieved through careful polishing, chemical etching, and vapor deposition processes that build up the reflective layer atom by atom. Even with these advanced techniques, perfect mirrors remain an ideal that we can approach but never fully achieve. The quantum mechanical uncertainty principle itself places fundamental limits on how perfectly we can control the position of atoms on a surface. Temperature fluctuations cause atoms to vibrate around their equilibrium positions, creating a form of thermal roughness that can never be completely eliminated. Interestingly, some of the most important advances in mirror technology have come from understanding and working with these imperfections, rather than trying to eliminate them completely. Adaptive mirrors used in astronomy, for example, can change their shape thousands of times per second to compensate for atmospheric turbulence. These mirrors use controlled imperfections, deliberate changes in surface shape to improve the quality of the reflected image. The study of surface imperfections has also led to new understanding of how light interacts with matter at the nanoscale. Surface plasmons, those collective oscillations of electrons we discussed earlier, can be excited more efficiently at surface defects and irregularities. This has led to new technologies that use carefully designed surface structures to enhance light-matter interactions for applications in sensors, solar cells, and other optical devices. What's particularly fascinating is that the quantum nature of light makes it sensitive to surface features that are much smaller than the wavelength of the light itself. Through subtle quantum mechanical effects, light can feel the atomic structure of the surface, leading to slight changes in the reflection properties that depend on the specific arrangement of atoms at the surface. This sensitivity to atomic scale structure means that every mirror has its own unique quantum signature, subtle pattern of reflection characteristics that depends on the precise arrangement of atoms on its surface. While these differences are usually too small to detect with ordinary instruments, they represent the fundamental quantum mechanical nature of the reflection process. As we contemplate the surface of a mirror, we're reminded that even the most mundane objects reveal extraordinary complexity when examined closely enough. The simple act of looking at your reflection involves countless quantum interactions with individual atoms, each one contributing to the faithful reproduction of your image. The imperfections that exist at the atomic level don't detract from the mirror's performance. They're part of the rich quantum mechanical symphony that makes reflection possible, long before humans ever dreamed of perfect mirrors. Nature had already mastered the art of reflection. Picture, if you will, a still mountain lake at dawn, its surface so perfectly calm that it becomes indistinguishable from the sky above. This is where our story of mirrors truly begins, not in some ancient workshop, but in the quiet moments when our ancestors first gazed upon their own faces, reflected in pools of water. Imagine that first startling moment of recognition. A human being, perhaps tens of thousands of years ago, leaning over a spring to drink, only to find another face staring back from the depths. The shock, the wonder, the slow realization that this mysterious other was somehow themselves. It must have felt like discovering magic. And in many ways, it was. These early water mirrors were perfect teachers, showing us the fundamental nature of reflection without revealing its secrets. The surface of still water acts as a mirror because of the way light behaves at the boundary between two different materials, in this case, air and water. When light travels from air and hits the water surface at just the right angle, much of it bounces back instead of passing through, carrying with it the image of whatever was above. But water mirrors were fragile things. A single ripple could shatter the reflection into 1,000 dancing fragments, each one carrying a piece of the image before scattering it into chaos. Our ancestors learned to read these watery mirrors carefully, choosing the stillest moments of dawn or dusk when the air was calm and the water lay like a sheet of glass. That the ancient Egyptians, those masterful observers of the natural world, were among the first to capture this magic in solid form. Around 4000 BCE, they began polishing pieces of obsidian, volcanic glass formed in the Earth's fiery depths, until they achieved a surface so smooth that it could hold a reflection as surely as any pool. These obsidian mirrors were treasures beyond measure, objects of both practical use and spiritual significance. Think about the patience required to create such a mirror. An artisan would take a piece of raw obsidian, its surface rough and clouded, and begin the slow process of grinding and polishing. Hour after hour, day after day, they would work the stone against increasingly fine abrasives, each pass removing microscopic imperfections, until the surface became smooth enough to trap light and send it back in organized patterns. The Egyptians understood something profound about mirrors that we sometimes forget today. They were not just tools for vanity, but windows into the soul. In their mythology, mirrors were associated with the goddess Hathor, who was both the goddess of love and the protector of the dead. They believed that mirrors could capture not just images, but something deeper, the essence of the person. Reflected. Within, as civilizations grew and trade routes expanded, the knowledge of mirror making spread across the ancient world. The Greeks and Romans developed techniques for polishing bronze and silver into reflective surfaces, creating mirrors that were both beautiful and functional. These metal mirrors represented a quantum leap in our understanding of reflection. They were more durable than obsidian, brighter than polished stone, and could be shaped into forms that enhanced their reflective properties. The Romans, with their engineering prowess, discovered that the key to a perfect metal mirror lay in the final stages of polishing. They developed techniques using increasingly fine abrasives, finishing with rouge, a powder made from iron oxide that could create a surface so smooth it approached the molecular level. When light hit these perfectly polished surfaces, it had no choice but to reflect back in precise, organized patterns. But perhaps the most remarkable development in mirror history came from an unexpected source, the Islamic world of the Middle Ages. In the workshops of Damascus and Baghdad, craftsmen began experimenting with a revolutionary new technique, backing glass with thin layers of metal. This innovation, which would eventually lead to the mirrors we know today, represented a profound understanding of how light behaves at the interface between different materials. The process was delicate and required extraordinary skill. Craftsmen would take sheets of glass, itself a marvel of medieval technology, and carefully apply a thin layer of silver or tin to one surface. The glass protected the metal from oxidation, while allowing light to pass through to the reflective layer beneath. When light entered the glass and hit the metal backing, it would reflect back through the glass, creating an image of startling clarity and brightness. These early glass mirrors were magical objects, literally worth their weight in gold. They were so valuable that they were often used as diplomatic gifts between rulers, symbols of technological prowess and cultural sophistication. The techniques for making them were closely guarded secrets, passed down through generations of craftsmen who understood that they were the keepers of something precious. the ability to trap light and bend it to human will. The Renaissance brought new advances in mirror making, particularly in Venice, where the island of Murano became the mirror-making capital of the world. Venetian craftsmen developed techniques for creating larger, clearer mirrors than had ever been possible before. They learned to make glass so pure it was nearly invisible, and to apply silver backing so evenly that the resulting mirrors showed no distortion or cloudiness. But it was in the halls of Versailles that mirrors truly came into their own as symbols of power and beauty. The famous Hall of Mirrors, completed in 1684, contained 357 mirrors arranged in 17 arches, each one reflecting light from the gardens outside and multiplying it into a dazzling display of brilliance. Visitors reported feeling overwhelmed by the sheer luminosity of the space, as if they had stepped into a world made entirely of light. The creation of the Hall of Mirrors represented more than just artistic achievement. It was a testament to human mastery over light itself. Each mirror was a triumph of technology, requiring the coordination of glassmakers, metalworkers, and optical craftsmen working in perfect harmony. The mirrors didn't just reflect light, they orchestrated it, creating patterns and intensities that transformed the very nature of interior space. To truly understand how mirrors work, we must journey into a realm invisible to our eyes, the atomic world where matter reveals its most fundamental secrets. Imagine, if you will, that you could shrink yourself down to the size of an atom and walk along the surface of a mirror. What you would discover there would change forever how you think about reflection at the atomic level. A mirror's surface is not the smooth, perfect plane it appears to be to our eyes. Instead, it's a landscape of atoms arranged in precise patterns, each one vibrating with thermal energy, each one interacting with its neighbors through forces that operate on scales so small they defy our everyday understanding. Yet it is precisely this atomic architecture that gives mirrors their power to capture and redirect light. The atoms in a mirror's reflective surface are not randomly scattered like pebbles on a beach. Instead, they form what scientists call a crystal lattice, a three-dimensional pattern that repeats itself with mathematical precision throughout the material. In a silver mirror, for example, the silver atoms arrange themselves in a face-centered cubic structure, with each atom surrounded by 12 nearest neighbors in a pattern that extends in all directions. This crystalline structure is crucial to understanding how mirrors work. When light waves encounter this orderly arrangement of atoms, they interact with the electrons that orbit each atomic nucleus. These electrons, confined to specific energy levels by the laws of quantum mechanics, can absorb and re-emit light in ways that depend entirely on the precise arrangement of atoms. In the crystal dot, picture the electrons in a mirror's surface as tiny dancers, each one choreographed by the quantum rules that govern their behavior. When a photon of light strikes an electron, it doesn't simply bounce off like a ball hitting a wall. Instead, the electron absorbs the photon's energy, jumps to a higher energy level, and then almost instantly falls back down, re-emitting the photon in the process. This happens billions of times per second, with countless electrons participating in this quantum dance. But here's where the magic truly happens. The crystalline structure of the mirror ensures that all these individual quantum interactions add up in a very specific way. The electrons don't re-emit photons randomly in all directions. Instead, the orderly arrangement of atoms creates what physicists call constructive interference, where the re-emitted photons combine to produce a coherent reflected beam that preserves the original image. This is why a mirror made of randomly arranged atoms would not produce a clear reflection. The quantum interactions would still occur, but without the organizing influence of the crystal structure. The re-emitted photons would scatter in all directions, creating a diffuse glow rather than a sharp image. The crystal lattice acts like a conductor leading an orchestra, ensuring that all the individual quantum musicians play in perfect harmony. The efficiency of this process is remarkable. In a high-quality silver mirror, more than 95% of the incident light is reflected back in an organized pattern, with less than 5% being absorbed or scattered. This means that nearly every photon that hits the mirror surface participates in the quantum dance and emerges as part of the reflected image. It's a testament to the incredible precision of nature's atomic architecture. Different metals create mirrors with different properties because of their unique atomic structures and electron configurations. Silver, with its particular arrangement of electrons, reflects light across the entire visible spectrum with remarkable efficiency, which is why silver mirrors appear colorless and bright. Gold, by contrast, absorbs blue light more readily than red, giving gold mirrors their characteristic warm, yellowish tint. Aluminum, the metal used in most modern mirrors, offers a different set of properties. Its crystal structure and electron configuration make it highly reflective across a broad range of wavelengths, from the ultraviolet through the visible spectrum and into the infrared. This makes aluminum mirrors ideal for applications where broad-spectrum reflection is important, such as in telescopes and scientific instruments. The surface of a mirror must be incredibly smooth for this quantum dance to work properly. If the atomical flatness is disrupted by scratches, impurities, or oxidation, the careful orchestration of quantum interactions breaks down. Photons that should be reflected in an organized pattern instead scatter randomly, creating cloudy or distorted regions in the mirror's surface. This is why mirrors degrade over time. The perfectly arranged atoms at the surface slowly become disordered through chemical reactions with the atmosphere, mechanical wear, or thermal stress. What begins as a perfect crystal gradually becomes less organized, and the mirror loses its ability to coordinate the quantum dance of reflection. The silver backing of an old mirror might develop dark spots where the crystal structure has been compromised, creating areas where reflection is weak or non-existent. Modern mirror-making techniques have become incredibly sophisticated in their attempts to preserve this atomic perfection. Mirrors are now made in ultra-clean environments with protective coatings that prevent oxidation and contamination. Some high-end mirrors use multiple layers of different materials, each one tuned to optimize specific aspects of the reflection process. The quantum nature of mirror reflection reveals something profound about the relationship between light and matter. At the deepest level, there is no sharp distinction between the two. They are different aspects of the same underlying quantum reality. When light interacts with the electrons in a mirror, it temporarily becomes part of the material structure before being released back into space. For that brief moment, the light exists as an excitation in the electron sea of the metal, a quantum state that bridges the gap between electromagnetic radiation and solid matter. Within the seemingly simple structure of a mirror lies an architecture as complex and beautiful as any cathedral. To understand this architecture, we must explore the crystalline world where atoms arrange themselves in patterns that have persisted for billions of years, creating structures that can trap and redirect light with mathematical precision. Imagine holding a perfect crystal in your hands, perhaps a piece of quartz or a fragment of salt. What you're holding is not just a collection of atoms, but a three-dimensional poem written in the language of geometry. The atoms have arranged themselves according to principles that minimize energy while maximizing stability, creating patterns that repeat endlessly throughout the crystal structure. In the silver backing of a mirror, this crystalline architecture takes on a particularly elegant form. The silver atoms arrange themselves in what crystallographers call a face-centered cubic structure. Picture a cube with silver atoms at each corner and additional atoms at the center of each face. This pattern repeats throughout the entire thickness of the mirror's reflective layer, creating a three-dimensional lattice that extends for millions of atomic layers. This cubic symmetry is not arbitrary. It represents the most efficient way for silver atoms to pack together while maintaining the electronic properties that make silver such an excellent reflector. Each silver atom in this structure is surrounded by 12 nearest neighbors, arranged in a pattern that maximizes the overlap of electron orbitals while minimizing repulsive forces between atomic nuclei. The beauty of this arrangement becomes clear when we consider how it affects the behavior of electrons. In a single silver atom, electrons occupy discrete energy levels, confined to specific orbitals around the nucleus. But when millions of silver atoms come together in a crystal lattice, these individual energy levels merge into what physicists call energy bands, continuous ranges of allowed electron energies that extend throughout the entire crystal. The most important of these energy bands for mirror function is the conduction band, where electrons are free to move throughout the crystal structure. In silver, this conduction band is partially filled with electrons that can respond almost instantaneously to electromagnetic radiation. When light hits the mirror surface, these free electrons can absorb photons and re-emit them in a process that preserves the coherence and direction of the original light wave. The crystalline structure ensures that this electron response is highly organized. The regular spacing of atoms creates a periodic potential that guides the motion of electrons throughout the crystal. This periodicity is crucial. It's what allows the mirror to maintain phase relationships between different parts of the reflected wave, ensuring that the image remains sharp and undisturbed. Consider what happens when light encounters this crystalline architecture. The electromagnetic field of the light wave extends over many atomic spacings, encompassing thousands of silver atoms simultaneously. Each atom contributes to the overall response, but the contributions are coordinated by the underlying crystal structure. The result is a collective response that is far more powerful and precise than what any individual atom could achieve alone. This collective behavior is an example of emergence, a phenomenon where the properties of a system exceed the sum of its parts. No single silver atom is particularly reflective, but when millions of them are arranged in the proper crystalline pattern, they create a mirror capable of reflecting light with remarkable fidelity. The whole truly becomes greater than the sum of its parts. The perfection of this crystalline architecture is what distinguishes a high-quality mirror from a poor one. In a perfect crystal, the atomic arrangement is identical throughout the entire structure, with no disruptions or irregularities. Light hitting any part of such a mirror will encounter the same atomic environment and will be reflected in exactly the same way. Real mirrors, however, are never perfectly crystalline. They contain defects, places where the regular atomic arrangement is disrupted by impurities, grain boundaries, or crystal dislocations. These defects scatter light in random directions, reducing the mirror's overall reflectivity and creating slight cloudiness or distortion in the reflected image. The art of mirror making lies largely in minimizing these crystalline defects. Modern mirrors are created under carefully controlled conditions, with pure materials and precise temperature control to encourage the formation of large, well-ordered crystal grains. The backing material is often deposited slowly onto the glass substrate, allowing atoms time to find their optimal positions in the crystal lattice. Some of the most sophisticated mirrors use techniques borrowed from the semiconductor industry to create nearly perfect crystalline structures. These mirrors can achieve reflectivities approaching 99.9%, meaning that less than 1 photon in 1,000 is lost to absorption or scattering. Such precision requires crystalline perfection on an almost unimaginable scale. The atomic arrangement must be maintained with sub-nanometer precision across areas measured in square meters. The crystalline architecture of mirrors also determines their spectral properties, which wavelengths of light they reflect most efficiently. The spacing between atoms in the crystal lattice creates natural resonances that favor certain wavelengths over others. Silver mirrors, for example, reflect visible light very efficiently because the atomic spacing in silver crystals is well matched to the wavelengths of visible photons. This relationship between crystal structure and optical properties has led to the development of specialized mirrors for specific applications. Mirrors designed for use with infrared light might use different crystal structures or different materials entirely, optimized for the longer wavelengths of infrared radiation. Similarly, mirrors for ultraviolet applications require crystal structures that can handle the higher energy of UV photons without degrading. The crystalline architecture of mirrors connects us to some of the deepest principles of physics and chemistry. The same forces that determine how atoms bond together in molecules also determine how they arrange themselves in crystals. The same quantum mechanical principles that govern the behavior of electrons in atoms also govern their behavior in the extended states of crystal lattice. In essence, every mirror is a window into the fundamental nature of matter itself. The organized ranks of atoms in its crystalline structure represent one of nature's most elegant solutions to the problem of how to arrange matter in space. The way these atoms interact with light reveals the quantum mechanical principles that govern all electromagnetic phenomena, and the precision with which modern mirrors can be made demonstrates humanity's growing mastery over the atomic world. Deep within the metallic heart of every mirror lies a memory, not the kind of memory that stores information, but a more fundamental kind of memory that remembers how to interact with light. This memory is encoded in the electronic structure of the metal itself, in the vast sea of electrons that gives metals their distinctive properties and their ability to reflect light with such remarkable efficiency. To understand this electronic memory, we must first appreciate what makes metals different from other materials. In most substances, electrons are tightly bound to specific atoms, confined to narrow energy levels that prevent them from moving freely through the material. But in metals, something remarkable happens. The outer electrons from each atom contribute to a shared pool, creating what physicists call a sea of electrons that extends throughout the entire metallic structure. This electron sea is not a chaotic collection of particles wandering randomly through space. Instead, it's a highly organized quantum system where electrons occupy specific energy states according to the rules of quantum mechanics. At absolute zero temperature, these electrons would fill all available energy levels up to a maximum energy called the Fermi level, creating a sharp boundary between occupied and unoccupied states. But mirrors don't operate at absolute zero. They exist in our everyday world, where thermal energy constantly agitates the electron sea. At room temperature, some electrons near the Fermi level have enough thermal energy to jump to higher energy states, creating a small population of mobile, electrons that can respond quickly to external electromagnetic fields. These are the electrons that give metals their ability to conduct electricity and reflect light. When light hits a metal surface, it encounters this electron sea and interacts with it in a process that reveals the quantum nature of both light and matter. The oscillating electric field of the light wave pushes and pulls on the free electrons, causing them to accelerate back and forth in response to the electromagnetic radiation. This acceleration of charged particles creates new electromagnetic waves that propagate away from the metal surface, the reflected light that forms the mirror image. The remarkable thing about this process is how faithfully the electron sea reproduces the original light wave. Each point on the metal surface responds to the local electromagnetic field, creating a reflection that preserves not just the intensity of the light, but also its phase, relationships, and polarization. It's as if the electron sea has a perfect memory of the electromagnetic field that disturbed it, and it recreates that field in the reflected wave. This electronic memory is not perfect, however. Some of the energy from the incident light is absorbed by the metal, causing electrons to jump to higher energy states or creating vibrations in the atomic lattice. The absorbed energy is eventually dissipated as heat, which is why mirrors can become warm when exposed to intense light. The efficiency of the reflection process depends on how well the metal's electronic structure is matched to the frequency of the incident light. Silver, the metal most commonly used in high-quality mirrors, has an electronic structure that is nearly perfectly suited for reflecting visible light. The energy levels in silver are arranged in such a way that visible light photons can easily drive electrons from occupied to unoccupied states, creating the oscillating currents that produce reflected light. At the same time, the energy required for these transitions is low enough that most photons are re-emitted rather than absorbed. This electronic memory also explains why different metals produce mirrors with different colors. Gold, for example, has electronic transitions that preferentially absorb blue light while reflecting red and yellow light efficiently. This gives gold mirrors their characteristic warm, yellowish appearance. The electron sea in gold remembers blue light differently than red light, treating the two wavelengths according to its own internal electronic structure. The depth of this electronic memory is remarkable. Light doesn't just interact with the surface atoms of a metal, it penetrates into the material to a depth called the skin depth, which for visible light in metals is typically only a few tens of nanometers. Within this thin surface layer, millions of electrons participate in the reflection process, each one contributing to the collective response that creates the mirror image. This collective nature of the reflection process is what gives mirrors their stability and reliability. Even if individual atoms are displaced or a few electrons are scattered, the overall response of the electron sea remains essentially unchanged. The mirror's electronic memory is distributed among so many particles that local disturbances have little effect on the overall reflection properties. Modern research has revealed that this electronic memory can be modified and controlled in remarkable ways. By creating thin films with precisely controlled thicknesses and compositions, scientists can tune the electronic properties of mirrors to optimize their performance for specific applications. Some mirrors now use multiple layers of different metals, each one contributing its own electronic memory to create reflection properties that would be impossible with a single material. The study of how light interacts with the electron sea in metals has led to an entire field of physics called plasmonics. When light hits a metal surface under certain conditions, It can create collective oscillations of the electron sea called surface plasmons. These plasmons can be thought of as ripples in the electron sea that propagate along the metal surface, carrying energy and information in ways that are fundamentally different from ordinary light waves. Surface plasmons represent a kind of hybrid state between light and matter. They are neither purely electromagnetic waves nor purely electronic excitations, but something in between. They exist only at the interface between the metal and the surrounding medium, and they can be excited and controlled by carefully designed mirror structures. This has led to new technologies for manipulating light on scales smaller than the wavelength of light itself. The electronic memory of metals also has implications for the fundamental nature of reflection. When we look in a mirror, we see an image that appears to be located behind the mirror surface, but this image is not really there. It's a reconstruction created by the electronic memory of the metal. The electron sea has absorbed information about the light field in front of the mirror and used that information to create a new light field that appears to come from behind the mirror. This process of information transfer from the incident light to the reflected light is what allows mirrors to preserve images with such fidelity. The electronic memory of the metal acts like a quantum mechanical recording system, capturing the amplitude, phase, and polarization of the incident light and playing it back in the reflected beam. The fidelity of this recording depends on while the metal's electronic structure matches the characteristics of the light being reflected in the deepest sense. Every mirror is a testament to the quantum nature of matter and light. The electronic memory that enables reflection is a direct consequence of the wave-particle duality of electrons and the quantum mechanical principles that govern their behavior in solids. When we look in a mirror, we are witnessing a quantum mechanical process that connects the macroscopic world of everyday experience to the microscopic world of atoms and electrons. Light, in all its magnificent complexity, comes to us not as a single, uniform phenomenon, but as a symphony of wavelengths, each one carrying its own unique signature and interacting with mirrors in its own distinctive way. To truly understand the story of mirrors, we must listen to this symphony and learn how different wavelengths dance with the metallic surfaces that reflect them. Imagine light as a vast ocean, with waves of different sizes rolling endlessly toward the shore. The smallest waves, with wavelengths measured in fractions of a micrometer, carry the violet and blue light that paints the sky. Longer waves bring us the greens and yellows of sunlit meadows, while the longest visible waves carry the deep reds of sunset. Each wavelength has its own personality, its own way of interacting with the world around it. When these waves encounter a mirror, they don't all behave identically. The electronic structure of the mirror's metallic surface responds differently. Two different wavelengths, creating a complex interplay between the incoming light and the electron sea that will reflect it. This wavelength-dependent behavior is what gives mirrors their unique optical characteristics and determines how faithfully they can reproduce the colors of the world. In a perfect silver mirror, the response to different wavelengths is remarkably uniform across the visible spectrum. The electronic structure of silver is such that it can efficiently reflect wavelengths, from deep violet at 400 nanometers to deep red at 700 nanometers with nearly equal efficiency. This is why silver mirrors appear colorless. They don't favor any particular wavelength over others, giving us reflections that preserve the natural color balance of the scenes they capture, but venture beyond the visible spectrum, and the story becomes more complex. In the ultraviolet region, where wavelengths are shorter and photon energies are higher, silver begins to show its limitations. The higher energy of UV photons can excite electrons in silver to higher energy states, leading to increased absorption and reduced reflection. This is why silver mirrors appear to dim when viewed under ultraviolet light. The electronic memory of the metal is less efficient at these shorter wavelengths. At the other end of the spectrum, in the infrared region, where wavelengths are longer and photon energies are lower, silver again shows exceptional performance. The free electrons in silver can easily follow the slower oscillations of infrared light, creating efficient reflection well into the far infrared. This makes silver mirrors valuable for applications involving heat radiation, where the ability to reflect infrared wavelengths is crucial. The wavelength-dependent behavior of mirrors becomes even more fascinating when we consider materials other than silver. Aluminum, the most common mirror coating in modern applications, shows a different spectral response. Unlike silver, aluminum reflects ultraviolet light quite efficiently, making it the material of choice for mirrors used in UV applications. However, aluminum's reflection efficiency drops off more quickly in the infrared compared to silver. Gold presents yet another spectral personality. The electronic structure of gold creates a strong absorption band in the blue-green region of the spectrum, around 500 nanometers. This means that gold mirrors preferentially absorb blue and green light, while reflecting red and yellow wavelengths efficiently. The result is the characteristic warm, golden color of gold mirrors, not because gold emits golden light, but because it selectively removes the cooler colors from the reflected spectrum. This wavelength selectivity of different metals has profound implications for how we perceive colors in mirrors. When you look at your reflection in a silver mirror, you see colors that are very close to their natural appearance because silver reflects all visible wavelengths with nearly equal efficiency. But look at the same scene in a gold mirror, and the colors shift toward the warm end of the spectrum, creating a sunset-like effect that can be quite flattering, but is not spectrally accurate. The physics behind these wavelength-dependent effects lies in the quantum mechanical nature of electron excitations in metals. Each metal has its own unique electronic structure, with energy levels and transition probabilities that determine how efficiently it can reflect different wavelengths. When a photon hits the metal surface, it can either be reflected elastically, bouncing off without losing energy, or it can be absorbed, exciting an electron to a higher energy state. The probability of absorption versus reflection depends on the availability of suitable electronic states at the energy corresponding to the photon's wavelength. If there are many available states at that energy, absorption is likely and reflection is reduced. If there are few available states, the photon is more likely to be reflected. This is why the reflection spectrum of a metal provides a direct window into its electronic structure. Modern mirror technology has learned to exploit these wavelength-dependent effects to create mirrors with tailored spectral properties. By combining different metals in thin layers or by alloying metals together, engineers can create mirrors that reflect specific wavelengths with high efficiency while absorbing others. This has led to the development of specialized mirrors for laser applications, astronomical telescopes, and scientific instruments. One of the most remarkable developments in this field is the creation of dielectric mirrors, mirrors that use no metal at all, but instead rely on the interference of light waves in carefully designed stacks of transparent materials. These mirrors can achieve reflection efficiencies approaching 100% for specific wavelengths, far exceeding what is possible with metallic mirrors. However, they work only over narrow wavelength ranges and are much more complex to manufacture. The wavelength dependence of mirror reflection also has important implications for the preservation of information in reflected light. When we look in a mirror, we're not just seeing light, we're seeing information about the world that has been encoded in the wavelength distribution of that light. The fidelity with which a mirror preserves this wavelength information determines how accurately it can reproduce the colors and details of the original scene. This becomes particularly important in applications where color accuracy is crucial, such as in art galleries, museums, or photography studios. The choice of mirror coating can significantly affect how colors appear in the reflected light, and understanding the wavelength-dependent properties of different materials is essential for creating environments where colors are reproduced with maximum fidelity. The story of wavelengths and mirrors also connects to some of the deepest questions in physics about the nature of light and matter. The fact that different wavelengths interact differently with the same material reveals the quantum mechanical nature of electromagnetic radiation. Each wavelength corresponds to a specific photon energy and the interaction of these photons. With the electronic structure of the mirror, material is governed by the fundamental laws of quantum mechanics. In recent years, researchers have discovered that the wavelength dependence of mirror reflection can be controlled and manipulated in ways that were previously impossible. By structuring mirror surfaces on scales comparable to the wavelength of light, they can create mirrors that exhibit properties that don't exist in natural materials. These metamaterial mirrors can reflect light in ways that seem to violate our everyday intuition about how mirrors should behave. As we continue to explore the relationship between light and mirrors, we're discovering that the wavelength dimension offers endless possibilities for innovation and discovery. Each new wavelength regime we explore, from the deep ultraviolet to the far infrared, from radio waves to X-rays, reveals new aspects of how light and matter interact, and new possibilities for creating mirrors with previously unimaginable properties. As we continue our gentle journey through the world of mirrors and light, we arrive at something truly magical, the realm where straight lines become curves, and reality begins to bend in the most beautiful ways. Imagine, if you will, holding a spoon up to your face and watching your reflection dance between right side up and upside down as you move it closer and farther away. This simple kitchen utensil becomes a gateway to understanding one of the most fascinating aspects of how light behaves when it encounters curved surfaces. The story of curved mirrors begins with the same fundamental principle. We've been exploring that light travels in straight lines until it encounters a boundary. But when that boundary is curved rather than flat, something extraordinary happens. Instead of creating a simple, faithful reflection like a flat mirror, curved mirrors gather light in ways that can magnify, shrink, invert, or even create multiple images of the same object. Think of a curved mirror as a collector of light rays, much like a gentle hand cupping water from a stream. When parallel rays of light hit a curved mirror, they don't simply bounce back in parallel lines. Instead, they converge or diverge, creating focal points where the light energy concentrates or spreads out. This focusing effect is what makes curved mirrors so powerful and so useful in everything from telescopes that peer into the depths of space to the tiny mirrors in our car headlights that help us see the road ahead. There are two main types of curved mirrors, each with its own personality and purpose. Concave mirrors, which curve inward like the inside of a bowl, are gatherers of light. They collect parallel rays and bring them together at a single point called the focal point. These mirrors have a way of making things appear larger when you're close to them, but smaller when you're far away. It's as if they're playing a gentle game with reality, stretching and compressing the image depending on where you stand. The mathematics behind this behavior is elegant in its simplicity. The focal length of a concave mirror, the distance from the mirror to the point where parallel rays converge, is exactly half the radius of curvature. This relationship, discovered centuries ago, allows us to predict exactly how a curved mirror will behave. But more than just numbers, this relationship tells us something profound about the nature of light itself and how it responds to the geometry of the surfaces it encounters. When you stand close to a concave mirror, closer than its focal length, something wonderful happens. The mirror can no longer bring the light rays from your face to a real focus behind the mirror. Instead, it creates what we call a virtual image, one that appears to be in front of the mirror, larger than life, and right side up. This is the magnifying effect you experience when you look into a makeup mirror or a shaving mirror. The mirror is essentially tricking your eyes into thinking you're seeing a larger version of yourself. But step back beyond the focal point, and the magic changes completely. Now the mirror can bring the light rays to a real focus, creating an image that appears upside down and often smaller than the original object. This might seem like a disadvantage, but it's actually incredibly useful. Every reflecting telescope, from the small ones in backyards to the massive ones in observatories, uses this principle to gather faint light from distant stars and galaxies, and bring it to a focus where it can be studied and photographed and photographed. The other type of curved mirror, the convex mirror, tells a different story altogether. Curving outward like the back of a spoon, these mirrors are spreaders of light. They take parallel rays and send them diverging outward, creating images that are always smaller than the original object, always right side up, and always appearing to be behind the mirror surface. These mirrors have a special superpower. They can show you a much wider field of view than a flat mirror of the same size dot. You encounter convex mirrors more often than you might realize. The round security mirrors in store corners, the passenger side. Mirrors on cars, which often carry the warning objects in mirror, are closer than they appear. And even the curved mirrors at dangerous intersections all use this principle. They sacrifice the ability to show things at their actual size in exchange for showing you much more of the world around you. The physics behind convex mirrors is equally fascinating, because they spread light out rather than concentrating it. They can never form a real image, one that could be projected onto a screen. Instead, they always create virtual images that appear to be behind the mirror surface. These images are always diminished in size, which is why that side mirror makes the car behind you look farther away than it actually is. But curved mirrors are just the beginning of our exploration into how light can be manipulated and controlled. The same principles that govern curved mirrors also apply to lenses' transparent materials that bend light through refraction rather than reflection. When light passes from one medium to another, like from air into glass, it changes direction slightly. This bending, or refraction, follows a precise mathematical relationship discovered by a Dutch scientist named Willebrord Snellius in the early 1600s. Snell's law, as it came to be known, tells us that when light hits the boundary between two materials at an angle, the amount it bends depends on the refractive indices of the two materials. The refractive index is essentially a measure of how much a material slows down light compared to its speed in a vacuum. Glass, for instance, has a refractive index of about 1.5, meaning light travels about 1.5 times slower in glass than in empty space. This slowing down of light is what causes the bending, and it's this bending that allows lenses to focus light just like curved mirrors do. A convex lens, thicker in the middle than at the edges, acts much like a concave mirror, gathering parallel rays and bringing them to a focus. A concave lens, thinner in the middle than at the edges, acts like a convex mirror, spreading light rays outward. The beauty of lenses lies in their ability to work with light passing through them rather than bouncing off them. This means we can stack multiple lenses together, each one further refining and controlling the light. This is the principle behind everything from eyeglasses that correct vision problems to the complex lens systems in cameras and telescopes that can capture incredibly detailed images of objects, both near and far. But perhaps the most intriguing aspect of curved mirrors and lenses is how they can create optical illusions that challenge our perception of reality. These aren't tricks or deceptions in the traditional sense, but rather natural consequences of the laws of physics, playing out in ways that our brains aren't quite prepared for. As we delve deeper into the story of mirrors and light, we encounter one of the most fascinating aspects of optics, the creation of illusions that seem to defy our everyday understanding of the world. These optical illusions aren't magic tricks or clever deceptions, but rather natural consequences of how light behaves when it encounters certain arrangements of mirrors, lenses, and other optical elements. Consider the simple act of looking at yourself in a funhouse mirror. The wavy, distorted reflection that greets you might seem comical, but it's actually a beautiful demonstration of how even small changes in the curvature of a mirror can dramatically alter the path of light rays. Each section of the mirror with a different curvature focuses or spreads light differently, creating a patchwork of magnified and diminished regions that combine to form that wonderfully distorted image. The science behind these distortions is rooted in the same principles we've been exploring. When a mirror's surface curves in multiple directions, different parts of your reflection are processed differently. Areas where the mirror curves inward will magnify that portion of your image, while areas that curve outward will compress it. The result is a reflection that maintains your basic shape and proportions, while stretching and compressing different parts in ways that seem impossible. But funhouse mirrors are just the beginning of how mirrors can create illusions. One of the most striking examples is the phenomenon of the mirage, where light itself seems to bend and twist in ways that create images of objects that aren't really there, or that appear to be in places they aren't. On a hot summer day, you might see what looks like a pool of water on the pavement ahead of you, complete with reflections of the sky and surrounding objects. But as you get closer, the water disappears, always seeming to be just a little farther ahead. This isn't your eyes playing tricks on you. It's the atmosphere itself, acting like a complex lens system. Hot air is less dense than cool air, and this difference in density creates a difference in refractive index. Light traveling through layers of air at different temperatures bends and curves, following paths that seem to defy logic. The water you see is actually an inverted image of the sky, created when light from above is bent so severely by the hot air near the ground that it appears to be coming from below. These atmospheric mirages can be incredibly complex and beautiful. In polar regions, where cold air lies beneath warmer air, superior mirages can make distant objects appear to float in the sky. Ships on the horizon might seem to be sailing upside down above the water, or distant mountains might appear to be hovering in mid-air. These effects are caused by the same physics that creates the shimmering water illusion on hot pavement, but in reverse. The study of these atmospheric optics reveals something profound about the nature of light and vision. Our brains are incredibly sophisticated at interpreting the light that reaches our eyes, but they rely on certain assumptions about how light behaves. When those assumptions are violated by unusual optical conditions, our perception can be dramatically altered. Another fascinating aspect of optical illusions involves the way multiple mirrors can interact with each other. When you place two mirrors at an angle to each other, they create multiple reflections that seem to stretch into infinity. Each mirror reflects not only the original object, but also the reflection from the other mirror, creating a recursive cascade of images that appears to go on forever. The number of reflections you see depends on the angle between the mirrors. If you place two mirrors at a 90-degree angle, you'll see 3 reflections of any object placed between them. At a 60-degree angle, you'll see 5 reflections. At a 45-degree angle, you'll see 7. There's a beautiful mathematical relationship at work here. The number of reflections equals 360 divided by the angle between the mirrors, minus 1. This principle is used in devices called kaleidoscopes, where mirrors arranged in a triangular configuration create beautiful, symmetrical patterns from simple objects. The multiple reflections combine to create patterns that seem far more complex and ordered than the random objects that create them. It's as if the mirrors are collaborating to find hidden symmetries and patterns in the world around us. But perhaps the most mind-bending optical illusions come from the realm of holography, where light itself is used to create three-dimensional images that seem to float in space. Unlike traditional photography, which captures only the intensity of light at each point, holography captures both the intensity and the phase of light waves. This additional information allows a hologram to recreate not just the appearance of an object, but also its three-dimensional structure. The physics of holography relies on the wave nature of light and the principle of interference. When two coherent light waves meet, they can either reinforce each other, constructive interference, or cancel each other out, destructive interference, depending on their relative phases. A hologram is created by recording the interference pattern between a reference beam of coherent light and light reflected from the object being holographed. When you illuminate a hologram with coherent light, the recorded interference pattern recreates the original light waves that came from the object. Your eyes receive light that behaves exactly as if it were coming from the original object, complete with all the depth cues and perspective changes that make three-dimensional vision possible. The result is an image that appears to have real depth and dimension, even though it's created by light patterns on a flat surface. This technology has applications far beyond the novelty holograms you might see on credit cards or in science museums. Holographic data storage can pack enormous amounts of information into tiny spaces by using the three-dimensional structure of light itself. Holographic microscopy can create detailed three-dimensional images of living cells and other microscopic objects. And holographic displays promise to revolutionize everything from entertainment to medical imaging. But even simpler optical arrangements can create stunning illusions. Consider the Pepper's ghost illusion, a technique that's been used in theaters for over a century to make ghostly figures appear and disappear on stage. This illusion uses a sheet of glass positioned at a 45-degree angle to the audience. When the ghost area below the stage is dark, the glass is invisible to the audience. But when lights illuminate the hidden area, the glass acts like a mirror, creating a reflection that appears to be floating on the main stage. The elegance of this illusion lies in its simplicity. By controlling the lighting, operators can make the ghost appear gradually, change its opacity, or make it disappear entirely. The audience sees what appears to be a supernatural apparition, but it's actually just the controlled reflection of light from a hidden area. This same principle is used in modern applications like teleprompters, where speakers can read text while appearing to look directly at their audience. Another category of optical illusions involves the manipulation of polarized light. Light waves normally vibrate in all directions perpendicular to their direction of travel, but polarized light vibrates in only one direction. Polarizing filters can block light waves that aren't aligned with their transmission axis, creating effects that seem to violate our expectations about how light behaves. When you look at a pond or lake through polarized sunglasses, you might notice that the reflections on the water surface become much dimmer or disappear entirely. This happens because reflected light is partially polarized, and the polarizing filter blocks much of it while allowing the light from underwater objects to pass through. The result is that you can see through the water surface much more clearly than you could with naked eyes. Some materials, like certain crystals and stressed plastics, can rotate the direction of polarized light. When viewed between crossed polarizing filters, these materials create beautiful patterns of color and light. The amount of rotation depends on the thickness of the material and the amount of stress it's under, creating a technique called photoelasticity that engineers use to visualize stress patterns in mechanical structures. The study of optical illusions reveals something fundamental about the nature of perception itself. Our brains don't simply receive passive reports from our eyes about the world around us. Instead, they actively interpret and process visual information, making assumptions and filling in gaps based on our past experiences and expectations. When optical phenomena violate these assumptions, we experience illusions that can be beautiful, surprising, or even unsettling. This relationship between physics and perception has profound implications for how we understand reality itself. The light that reaches our eyes has been shaped by countless interactions with the materials and phenomena it has encountered on its journey. Every reflection, refraction, and interference pattern carries information about the world, but that information must be decoded by our visual system to become meaningful. As our journey through the world of mirrors and light continues, we arrive at one of the most profound aspects of reflection, the way mirrors seem to hold memories of the light that has touched them. This isn't memory in the way we typically think of it, but rather the subtle ways that light interactions leave traces, patterns, and evidence of their encounters with reflective surfaces. Every photon that strikes a mirror and bounces back carries with it a story. The wavelength of the light tells us about its color and energy. The angle of incidence reveals the direction from which it came. The polarization states speak to the materials and processes it encountered along its journey. In this way, every reflection is both an ending and a beginning, the end of one photon's journey and the beginning of another's. Consider an ancient bronze mirror, polished smooth thousands of years ago, and still capable of creating clear reflections. Today, the light that bounces off this mirror is the same light that has been traveling through space for billions of years, but its interaction with the mirror creates something new. The bronze atoms in the mirror don't just passively reflect the light, they absorb it momentarily, allowing their electrons to dance to the rhythm of the electromagnetic waves before releasing it back into the world. This absorption and re-emission process happening in the tiniest fractions of a second, is what gives different mirrors their characteristic properties. A silver mirror reflects light differently than a bronze mirror, which reflects differently than an aluminum mirror. Each type of metal has its own unique arrangement of electrons, its own resonant frequencies, its own way of interacting with light. These differences are so subtle that they're often invisible to the naked eye, but they're there, embedded in the light itself. Modern science has learned to read these subtle signatures with incredible precision. Spectroscopy, the study of how matter interacts with light, can identify the exact composition of a material by analyzing the light it reflects, absorbs, or emits. When starlight travels across the galaxy and reflects off a planet's atmosphere, scientists can determine what gases are present in that atmosphere by studying the specific wavelengths of light that are missing or enhanced in the reflected spectrum. This same principle works on a much smaller scale. When light reflects off a soap bubble, the thin film of soap creates an interference pattern that depends on the thickness of the bubble wall. As the bubble evaporates and its walls become thinner, the colors shift and change, creating a dynamic display that maps the bubble's geometry in real time. The light itself becomes a measuring tool, revealing information about structures too small to see directly, but mirrors can hold memories in even more literal ways. In certain materials, exposure to light can create permanent changes in the structure of the material itself. Photochromic materials, like those used in self-darkening sunglasses, undergo chemical changes when exposed to ultraviolet light. These changes alter how the material reflects and transmits light, creating a kind of optical memory that persists until the material is returned to its original state. Even more remarkably, some materials can store complex optical information for later retrieval. In holographic data storage, interference patterns created by laser light are preserved in photosensitive materials. These patterns can encode not just simple images, but vast amounts of digital information when the stored hologram is illuminated. With the proper reference beam, it recreates the original light pattern, effectively reading back the stored information. The quantum nature of light adds another layer to this story of optical memory. When a photon is absorbed and re-emitted by an atom, there's a quantum mechanical relationship between the two events. The re-emitted photon carries information about the quantum state of the atom at the moment of absorption. This quantum entanglement between light and matter forms the basis for emerging technologies like quantum cryptography and quantum computing. In quantum cryptography, the polarization states of photons are used to encode information in ways that are theoretically impossible to intercept without detection. Any attempt to measure the photon's polarization necessarily changes its quantum state, alerting the sender and receiver that their communication has been compromised. The mirror-like interactions between light and matter at the quantum level create a kind of unhackable code based on the fundamental laws of physics. The concept of optical memory extends beyond individual mirrors to entire optical systems. When light travels through a complex arrangement of mirrors, lenses, and other optical elements, each component adds its own signature to the light. The final image or signal carries the accumulated history of all these interactions. Like a palimpsest, where each layer of text tells part of the story. This principle is used in optical communications, where information is encoded in the properties of light pulses that travel through fiber optic cables. Each pulse carries not just the intended information, but also traces of its journey through the optical system. Engineers have learned to use these traces to monitor the health of the communication network. detecting problems like bent fibers or contaminated connections by analyzing the subtle changes in the light signals. The astronomical applications of optical memory are particularly fascinating. When we look at distant galaxies through telescopes, we're not just seeing them as they are now, we're seeing them as they were millions or billions of years ago. The light that reaches us has been traveling through space for eons, carrying with it a frozen record of the conditions that existed when it was first emitted. But the journey of this ancient light doesn't end when it was first emitted. Along its path through the universe, it encounters gravitational fields that bend space-time itself, creating effects that Einstein predicted in his theory of general relativity. Massive objects like galaxies and galaxy clusters act like cosmic lenses, focusing and distorting the light from even more distant objects. By studying these gravitational lensing effects, astronomers can map the distribution of dark matter in the universe and probe the fundamental structure of space-time itself. The mirrors in our telescopes become the final step in this cosmic journey, gathering this ancient light and focusing it for our instruments to study. Each photon that reaches our detectors carries information not just about the object that emitted it, but about everything it encountered along its billions-year journey through the cosmos. The mirror becomes a kind of time machine, allowing us to peer back toward the beginning of the universe itself. This temporal aspect of reflection brings us to one of the most profound implications of mirror physics. Because light travels at a finite speed, every reflection we see is actually a glimpse into the past. When you look at yourself in a bathroom mirror, you're seeing yourself as you were a few billionths of a second ago. When you look at the moon in a telescope, you're seeing it as it was about 1.3 seconds ago. When you look at the sun's reflection in water, you're seeing it as it was about 8.3 minutes ago. This delay might seem negligible in everyday life, but it has profound implications for our understanding of simultaneity and the nature of time itself. Einstein's special theory of relativity showed us that there's no such thing as absolute simultaneity. Events that appear simultaneous to one observer may not be simultaneous to another observer moving at a different velocity. The speed of light sets a fundamental limit on how quickly information can travel from one place to another, making it impossible to know the true present state of distant objects. In this context, mirrors become more than just tools for reflection. They become gateways to understanding the fundamental structure of space-time itself. Every reflection carries with it information about the past, encoded in the properties of the light that creates it. By learning to read these optical memories, we gain insight not just into the objects we're studying, but into the nature of reality itself. As we continue our gentle journey through the world of mirrors and light, we find ourselves standing at the edge of a remarkable transformation. The humble mirror, once simply a tool for seeing our reflection, has evolved into something far more extraordinary. In the laboratories and research centers of today, mirrors have become the silent heroes of our most ambitious scientific endeavors, working tirelessly to push the boundaries of what we thought possible. Imagine, if you will, the vast mirrors of the Hubble Space Telescope, floating serenely in the darkness of space. These aren't the mirrors we know from our daily lives, but precision-crafted surfaces, so perfect that they can capture light that has traveled for billions of years across the cosmos. Each photon that reaches these mirrors carries with it a story. From the distant past, a whisper from stars that may no longer exist. The mirror doesn't just reflect this light. It preserves it, focuses it, and delivers it to us with such clarity that we can peer back through time itself. The making of these space mirrors is a meditation in patience and precision. In clean rooms where even the smallest speck of dust would be a catastrophe, craftsmen work with tools that can measure distances smaller than the wavelength of light itself. They polish surfaces to a smoothness that would make a still pond seem rough by comparison. The process can take months, even years, as each mirror is slowly shaped and perfected, molecule by molecule, until it achieves a flatness that varies by no more than a few atoms across its entire surface. But the revolution doesn't stop with telescopes. In the world of laser technology, mirrors have become the conductors of light orchestras, directing beams with such precision that they can perform surgery on individual cells or cut through steel with the delicacy of a surgeon's scalpel. These mirrors work in harmony with light waves, creating standing waves and interference patterns that can trap particles in midair, cool atoms to temperatures colder than the depths of space, or create holograms so realistic they seem to breathe with life. Consider the gentle miracle of laser eye surgery, where mirrors guide healing light into the most delicate part of our bodies. The eye, that window to our soul, can be reshaped and healed by light that has been carefully choreographed by mirrors. The laser beam, reflected and focused by a series of mirrors, can remove tissue one layer at a time, each pulse lasting only a few femtoseconds, a time so brief that light itself can barely travel the width of a human hair. Yet, in that impossibly short moment, the mirror has done its work, directing the light with such precision that it can correct vision that has been blurred for decades. In the world of quantum physics, mirrors have become the guardians of light's most mysterious properties. In laboratories around the world, scientists use mirrors to create quantum states of light that exist in multiple places at once, or to entangle photons in ways that Einstein himself called spooky action at a distance. These quantum mirrors don't just reflect light, they can modify its very nature, creating photons that are squeezed, twisted, or paired in ways that reveal the fundamental strangeness of our universe. The mirrors used in gravitational wave detectors represent perhaps the most sensitive instruments ever created by human hands. These mirrors, suspended in perfect isolation from vibrations, can detect movements smaller than 1/10,000th the width of a proton. When a gravitational wave passes through space, rippling the very fabric of reality, these mirrors feel the distortion and translate it into a signal that reveals the collision of black holes billions of light years away. The mirrors themselves become witnesses to the universe's most violent events, their reflective surfaces serving as the ultimate recording devices for the cosmos. In the realm of solar energy, mirrors have become the harvesters of our stars' endless bounty. Fields of mirrors, each one precisely angled and computer-controlled, track the sun across the sky like a field of technological sunflowers. They concentrate sunlight with such efficiency that they can melt salt to create thermal energy that lasts long after the sun has set. These mirrors don't just reflect light, they capture it, concentrate it, and transform it into the power that lights our homes and fuels our dreams of a sustainable future. The development of adaptive mirrors has brought us into an era where reflection itself can be controlled and modified. In real time, these mirrors, composed of thousands of tiny segments, can change their shape hundreds of times per second, correcting for atmospheric disturbances that would otherwise blur our view of the stars. They work like a constant, gentle massage for light, smoothing out the ripples and distortions that our atmosphere creates, allowing ground-based telescopes to achieve clarity that rivals those in space. As we delve deeper into the modern age of mirrors, we encounter something that would have seemed like pure magic to our ancestors: mirrors that can think. These aren't the passive reflectors of the past, but active surfaces that can process information, make decisions, and even learn from their experiences. The boundary between mirror and mind has begun to blur in ways that challenge our understanding of what it means to reflect. Digital mirrors represent the first steps in this transformation. These devices, found in modern cars and smart homes, don't just show us our reflection. They overlay information onto our image, creating a seamless blend of the physical and digital worlds. When you look into a smart mirror in your bathroom, you might see not just your face, but also the weather forecast, your calendar for the day, or your health metrics displayed as gentle overlays on your reflection. The mirror has become a window into both your physical appearance and your digital life. But the true revolution comes with the development of programmable mirrors, surfaces that can be controlled pixel by pixel to create any reflection desired. These mirrors use millions of microscopic elements, each capable of reflecting light in different directions or colors. They can transform a simple, reflective surface into a dynamic display, showing moving images, changing colors, or even creating the illusion of depth where none exists. The mirror becomes a canvas for light, painted not with pigments but with precisely controlled reflections. In the field of optical computing, mirrors have become the neurons of light-based brains. These systems use the reflection and interference of light beams to perform calculations at the speed of light itself. Instead of electrical signals flowing through silicon pathways, these computers use photons bouncing between mirrors to process information. The mirrors serve as both the memory and the processing elements, storing information in the form of standing wave patterns and performing calculations through the complex dance of interfering light waves. The development of metamaterial mirrors has opened up possibilities that seem to defy the laws of physics as we understand them. These artificial materials, composed of structures smaller than the wavelength of light, can bend and shape light in ways that natural materials cannot. They can create mirrors that reflect light backwards along the same path it came from, regardless of the angle of incidence. They can make objects appear invisible by bending light around them, or create the illusion of negative refractive index, where light behaves in ways that contradict our everyday experience. In the realm of virtual and augmented reality, mirrors have become the bridge between the physical and digital worlds. Special mirrors and reflective surfaces can create the illusion of three-dimensional objects floating in space, or allow us to see and interact with virtual environments as if they were real. These mirrors don't just reflect light, they create new realities, new experiences, and new ways of perceiving the world around us. The concept of smart mirrors extends beyond simple information display into the realm of health monitoring and personal care. These mirrors can analyze skin conditions, track changes in appearance over time, or even monitor vital signs through the subtle changes in skin color that occur with each heartbeat. They become our personal health assistants, using the power of reflection to help us understand and care for our bodies in ways that were never before possible. Holographic mirrors represent, perhaps, the most futuristic application of reflective technology. These devices can record and replay three-dimensional images with such realism that they seem to exist in the space in front of the mirror. The holographic information is stored in the interference patterns created by laser light, and when illuminated properly, these patterns reconstruct the original three-dimensional image, with perfect fidelity. The mirror becomes a time machine, preserving not just the appearance of objects, but their complete three-dimensional form. As we venture into the most mysterious realm of mirror science, we encounter phenomena that challenge our very understanding of reality. Quantum mirrors operate in a world where the familiar rules of reflection give way to the strange and wonderful principles of quantum mechanics. Here, mirrors don't just reflect light. They can create, destroy, and transform it in ways that seem to violate the classical laws of physics. The quantum properties of mirrors emerge from the fundamental fact that light itself is quantized. It comes in discrete packets called photons. When a photon encounters a mirror, it doesn't simply bounce off like a ball hitting a wall. Instead, it engages in a complex quantum interaction that can result in multiple possible outcomes. The photon might be reflected, absorbed, or even split into multiple photons of different energies. The mirror, in turn, recoils slightly from the interaction, conserving momentum in a dance that plays out at the quantum level. One of the most fascinating quantum mirror phenomena is the creation of squeezed light. Normally, light carries a certain amount of uncertainty. Its electric and magnetic fields fluctuate randomly around their average values. But quantum mirrors can redistribute this uncertainty, reducing the fluctuations in one property while increasing them in another. This squeezed light has remarkable properties. It can be used to make measurements that are more precise than anything possible with ordinary light, pushing the boundaries of what we can observe and measure in the quantum world. The phenomenon of quantum entanglement takes on new meaning when viewed through the lens of mirror science. When photons interact with certain types of quantum mirrors, they can become entangled, forever linked, in a way that measurement of one instantly affects the other, regardless of the distance between them. These quantum mirrors can create pairs of entangled photons, each carrying one half of a quantum correlation that Einstein famously called spooky action at a distance. The mirror becomes a source of quantum connections that transcend the classical limitations of space and time. In the realm of quantum information, mirrors have become the guardians of quantum states. Quantum mirrors can store quantum information in the form of photonic quantum states, preserving the delicate and entanglements that are essential for quantum computing and communication. These mirrors must be incredibly precise, maintaining their quantum properties even in the face of thermal noise and environmental disturbances that would destroy ordinary quantum states. The development of quantum error correction using mirrors represents one of the most sophisticated applications of reflective technology. These systems use multiple mirrors to create redundant quantum states, allowing quantum information to be preserved even when individual mirrors fail or become corrupted. The mirrors work together in a quantum network, constantly checking and correcting each other's quantum states to maintain the integrity of the stored information. Quantum mirrors also play a crucial role in the development of quantum teleportation, the process of transferring quantum states from one location to another without physically moving the particles involved. The mirrors don't teleport the particles themselves, but rather the quantum information that describes their states. This information can then be used to reconstruct the original quantum state in a new location, effectively teleporting the quantum properties from one place to another. The study of quantum mirrors has led to new insights into the nature of the vacuum itself. Even empty space, it turns out, is not truly empty, but filled with quantum fluctuations, virtual particles that briefly pop into existence before annihilating each other. Quantum mirrors can interact with these vacuum fluctuations, creating real photons from the apparent nothingness of empty space. This phenomenon, known as the dynamical Casimir effect, demonstrates that mirrors can literally create light from nothing, drawing energy from the quantum vacuum itself. As we stand at the threshold of tomorrow, the future of mirrors stretches before us like a vast, reflective landscape filled with possibilities we can barely imagine. The mirrors of the future will be more than passive reflectors. They will be active participants in our lives, intelligent surfaces that can think, learn, and adapt to our needs in ways that blur the boundary between technology and magic. Imagine mirrors that can change their properties at will, transforming from highly reflective surfaces to transparent windows, or even to displays that show any image or information desired. These programmable mirrors will use advanced materials that can alter their optical properties in response to electrical signals, chemical changes, or even direct mental commands. The mirror in your bedroom might serve as a reflective surface. In the morning, transform into a window to let in natural light during the day, and become a display screen for entertainment in the evening. The integration of artificial intelligence with mirror technology will create reflective surfaces that can recognize faces, interpret emotions, and respond to our needs before we even realize we have them. These smart mirrors will learn our daily routines, anticipate our preferences, and provide personalized feedback on everything from our health to our appearance. They might notice subtle changes in our skin tone that indicate health issues, or recognize when we're stressed and automatically adjust the lighting to create a more calming atmosphere in the field of medicine. The mirrors of the future will become diagnostic tools of unprecedented precision. Mirrors equipped with advanced sensors and imaging capabilities will be able to detect diseases at their earliest stages, monitor the progression of treatments, and even predict health problems before symptoms appear. These medical mirrors will use spectroscopic analysis to examine the chemical composition of our breath, saliva, or skin, providing instant health assessments that could revolutionize preventive care. The development of bio-integrated mirrors will create reflective surfaces that can interface directly with living tissue. These mirrors, made from biocompatible materials, could be implanted in the human body to provide internal imaging capabilities, or grown directly from engineered cells that naturally produce reflective proteins. The boundary between technology and biology will blur as mirrors become living, breathing parts of our bodies. Environmental mirrors will help us understand and respond to climate change by monitoring atmospheric conditions, tracking pollution levels, and even actively cleaning the air around them. These mirrors will use photocatalytic materials that can break down harmful pollutants when exposed to sunlight, turning every reflective surface into a small but significant contributor to environmental remediation. Solar mirrors will become more efficient and intelligent, automatically adjusting their positions and properties to maximize energy collection, while minimizing environmental impact. The mirrors of the future will also play a crucial role in space exploration and colonization. Lightweight, deployable mirrors will be used to create massive solar collectors that can power entire space stations or planetary colonies. These mirrors will be able to self-assemble from compact packages, unfurling like technological flowers, to capture and focus the energy of distant stars. They will serve as the foundations for space-based solar power systems that could beam clean energy back to Earth using precisely controlled laser beams. In the realm of communication, quantum mirrors will enable unbreakable encryption and instantaneous communication across vast distances. These mirrors will use quantum entanglement to create secure communication channels that are immune to eavesdropping, and quantum teleportation to transfer information faster than light itself. The mirrors will become the backbone of a new kind of internet, a quantum network that connects not just computers but quantum minds and artificial intelligences across the globe. The development of temporal mirrors will allow us to manipulate time itself, creating surfaces that can slow down, speed up, or even reverse the flow of time for light passing through them. These mirrors will use exotic materials and extreme conditions to bend space-time, creating temporal lenses that could allow us to see into the past or future. While still in the realm of theoretical physics, these concepts represent the ultimate evolution of mirror technology. As our journey through the world of mirrors and light draws toward its gentle conclusion, we find ourselves confronting questions that go far beyond the realm of physics and technology. The mirror, in all its forms, has become a profound metaphor for the human condition, a tool for understanding not just how light behaves, but how we perceive reality itself. The act of looking into a mirror is perhaps one of the most fundamentally human experiences. It is through reflection that we first become aware of ourselves as separate beings, distinct from the world around us. The mirror shows us not just our physical appearance, but our relationship to space, time, and existence itself. When we look into a mirror, we see ourselves as others see us, but also as we can never truly see ourselves from the outside, as an object in the world rather than the subject of our own experience. This duality of perspective has fascinated philosophers. For millennia, the mirror becomes a symbol of self-knowledge, but also of the fundamental impossibility of truly knowing ourselves. We can see our reflection, but we can never step outside of our own consciousness to see ourselves as we really are. The mirror shows us a reversed image, literally and perhaps metaphorically, of our true nature. In the quantum world, mirrors reveal even deeper philosophical truths about the nature of reality. The fact that light can exist in multiple states simultaneously until it is observed and measured suggests that reality itself might be more fluid and uncertain than we imagine. The mirror doesn't just reflect light, it participates in the creation of reality by forcing quantum systems to collapse into definite states. The act of reflection becomes an act of creation, a moment when possibilities become actualities. The phenomenon of quantum entanglement, mediated by mirrors, raises profound questions about the nature of separateness and connection. If two photons can be entangled through their interaction with a quantum mirror, remaining connected across vast distances, what does this tell us about the fundamental unity of the universe? Perhaps the mirror is showing us that separateness itself is an illusion, that all things are connected in ways we are only beginning to understand. The mirror also serves as a powerful metaphor for consciousness itself. Just as a mirror reflects light, consciousness reflects experience, creating an internal representation of the external world. But this reflection is not passive. It is active, interpretive, and creative. Our minds, like mirrors, shape and transform the information they receive, creating a unique version of reality that is both faithful to the original and distinctly our own. In the age of digital mirrors and smart surfaces, we are confronted with new philosophical questions about the nature of identity and authenticity. If mirrors can show us not just our current appearance, but our past selves, our potential futures, or even completely artificial versions of ourselves, what does it mean to be authentic? Are we becoming more true to ourselves through these enhanced reflections, or are we losing touch with our genuine nature. The mirror has always been associated with vanity and self-absorption, but perhaps this is too simplistic a view. The mirror can also be a tool for self-improvement, self-understanding, and even self-transcendence. When we look into a mirror, we have the opportunity to see ourselves, not just as we are, but as we might become. The reflection becomes a starting point for transformation, a moment of honest self-assessment that can lead to growth and change. The study of mirrors has also revealed the deep connections between art, science, and spirituality. The same principles that govern the reflection of light in a mirror also govern the creation of beauty in art, the perception of truth in science, and the experience of transcendence in spirituality. The mirror becomes a bridge between these different ways of understanding the world, showing us that they are not separate domains, but different reflections of the same underlying reality. As we develop more sophisticated mirror technologies, we are also developing new ways of understanding ourselves and our place in the universe. The mirror that can show us our quantum nature, our connection to distant stars, or our potential futures is not just a tool for seeing, it is a tool for becoming. It offers us new possibilities for growth, new ways of understanding our relationships with others, and new paths toward wisdom and enlightenment. The philosophical implications of mirror science extend to our understanding of truth itself. If mirrors can show us multiple versions of reality, if they can create illusions that are indistinguishable from truth, what does this tell us about the nature of objective reality? Perhaps the mirror is teaching us that truth is not a fixed, absolute thing, but a dynamic, interactive process that depends on the observer, the observed, and the act of observation itself. As we prepare to conclude our peaceful journey through the world of mirrors and light, we find ourselves witnessing an eternal dance that has been going on since the beginning of time. Light and reflection, waves and particles, reality and illusion, all dancing together in a cosmic ballet that encompasses everything from the smallest quantum fluctuation to the largest structures in the universe. This dance is not just a metaphor. It is a literal description of how the universe works. Every atom in your body, every photon of light that touches your skin, every mirror that reflects your image is participating in this cosmic choreography. The dance has no beginning and no end. It is a continuous flow of energy and information that connects all things in ways both subtle and profound. The mirror, in all its forms, is both a participant in this dance and a window through which we can observe it. When light strikes a mirror, it doesn't just bounce off randomly. It follows precise rules that govern the behavior of waves and particles. These rules are not arbitrary. They are expressions of the deepest principles that govern the structure of reality itself. The speed of light, that fundamental constant that appears in Einstein's famous equation, is not just a number. It is the tempo of the cosmic dance. It sets the rhythm for all electromagnetic phenomena. From the gentle oscillation of radio waves to the high-energy dance of gamma rays, the mirror, in reflecting light at this cosmic speed, becomes a keeper of time itself, preserving moments and memories in its silvered surface. The wave-particle duality of light, that strange quantum property that allows photons to behave like both waves and particles, is perhaps the most beautiful aspect of the cosmic dance. It shows us that reality is not fixed and rigid, but fluid and dynamic, capable of taking on different forms depending on how we choose to observe it. The mirror becomes a stage on which this duality plays out, sometimes reflecting light as a wave, sometimes as a stream of particles, always adapting to the needs of the moment. The principles of symmetry that govern the behavior of mirrors are also fundamental to the structure of the universe itself. The laws of physics are filled with symmetries, conservation laws that ensure that certain quantities remain constant, even as the universe changes and evolves. The mirror embodies these symmetries, reflecting not just light, but the underlying mathematical harmony that governs all of existence. As we look toward the future, we can see that the dance of light and reflection will continue to evolve and unfold in new and unexpected ways. The mirrors of tomorrow will be more than passive reflectors. They will be active participants in the cosmic dance, capable of creating new forms of light, new types of reflections, and new ways of understanding the universe. The quantum mirrors of the future will dance with individual photons, creating and destroying quantum states with the precision of a master choreographer. They will use the strange properties of quantum mechanics to create new forms of light that don't exist in nature. Beams of photons that are squeezed, entangled, or suspended in superposition states that defy our everyday understanding of reality. The biological mirrors of the future will dance with living systems, creating reflective surfaces that can grow, adapt, and evolve like living organisms. These mirrors will blur the boundary between the living and the non-living, between the natural and the artificial, creating new forms of beauty and functionality that we can barely imagine. The cosmic mirrors of the future will dance with the universe itself, creating reflective surfaces that span vast distances and harness the energy of stars and galaxies. These mirrors will help us understand the deepest mysteries of existence, from the nature of dark matter and dark energy to the possibility of parallel universes and alternate realities. But perhaps the most important dance of all is the one between the mirror and the observer, between the technology and the human heart. As mirrors become more sophisticated and capable, they will serve not just as tools for seeing and understanding, but as partners in the human journey toward wisdom and enlightenment. They will help us see not just what is, but what could be, not just who we are, but who we might become. The story of the mirror is ultimately the story of humanity itself, our desire to understand, to create, to connect, and to transcend the limitations of our physical existence. The mirror reflects not just light, but hope, not just images, but dreams, not just the present, but the infinite possibilities of the future. As we stand before the mirror of tomorrow, we see reflected back not just our own image, but the image of all humanity, curious, creative, and forever reaching toward the light. The mirror reminds us that we are not separate from the universe, but part of it, not observers standing outside of reality, but participants in the eternal dance of light and reflection that connects all things in the end. The mirror teaches us that reflection is not just a physical phenomenon, but a way of being in the world. To reflect is to be mindful, to be present, to be aware of the connections between ourselves and everything around us. The mirror, in all its forms, is a teacher of presence, a guide to awareness, and a reminder of the beauty and wonder that surrounds us at every moment. Thank you for staying with me through this peaceful journey into the story of a mirror, light in reverse. I hope that as you go about your day, you'll take a moment to pause whenever you encounter a mirror, whether it's the simple mirror in your bathroom, the rear-view mirror in your car, or the complex reflective surfaces of our modern world. Remember that each reflection is a small miracle, a moment when light reverses its course and shows us something new about ourselves and our universe. The dance of light and reflection continues around us always, invisible but ever present, connecting us to the cosmos and to each other in ways both subtle and profound. May your own journey through life be filled with moments of clarity and reflection, and may you always find in the mirror not just what you are, but what you might become. Until we meet again in another peaceful exploration of the wonders that surround us. Keep looking, keep wondering, and keep dancing with the light. If you enjoyed this gentle journey through the world of mirrors and light, I'd love to hear your thoughts in the comments below. What aspects of mirror science fascinated you most? Have you ever had a moment of wonder when looking into a mirror? Your reflections and experiences are always welcome here, and they help create a community of curious minds exploring the beautiful mysteries of our universe together. Remember to subscribe for more peaceful explorations of the science and wonder that surrounds us every day, and I'll see you in the next adventure. Sweet dreams, and may your reflections always show you the light.